Alright, we're recording, dude.
Chapter 30, problem number 43. One solenoid is centered inside of another. The outer one has a length of 50 centimeters and contains 6,750 coils, while the coaxial inner solenoid is 3 centimeters long and 1.2 centimeters in diameter and contains 15 coils. The current in the outer solenoid is changing at 49.2 amps per second. What is the mutual inductance of these solenoids? So the first thing I did for this problem was I wrote down the equation for mutual inductance to help me try to visualize this. And it's given right here, and we know that we need the flux. So that's the first thing I started to get. And you can use Ampere's law to get the flux of a solenoid equal to this, and the area of the small solenoid, cross-sectional area, is equal to this. So then you get this, and this would be your flux. And you plug in the flux here into the mutual inductance equation. And once you do that, a bunch of your I's start canceling out. It turns out really nice. And you get that the mutual inductance is 2.88 microhenries. And then we can use this formula for EMF of mutual inducting coils, which states that the mutual inductance is equal to the rate of change of the EMF of one of the coils is equal to the mutual inductance times the rate of change of the current in the second coil. And this makes sense because in terms of inductance, especially mutual inductance, if you wanted to get the EMF from one of them, you don't want to use the same current for the first one. Yep.
Alright.
And that's number 43.
Yeah, I followed along with that pretty well.
Thank you. Now we're on number 49. What would have to be the self-inductance of a solenoid for it to store 10 joules of energy when a 2 amp current runs through it? If this solenoid cross-sectional diameter is 4 centimeters, and you could wrap its coil to a density of 10 coils per millimeter, how long would that solenoid be? Is this a realistic length for an ordinary laboratory use? Okay, so this equation here gives the energy stored inside of a capacitor in a circuit. And the potential energy equals to 1/2 the inductance times current squared. And we're given that the energy is equal to 10 joules, and our current is 2. So by plugging it in, we get our inductance is equal to 5 henries. And for the next part, it was actually a lot trickier for me. I don't know if I did my work correctly, but we know the density, we know the cross-sectional area, or cross-sectional diameter, excuse me. And so we have to relate the density to an area somehow. And to help do this, we wanted to know the number of turns inside of it to help give us an idea of how long it is, I believe. Because if we know the number of turns and we know the length, so I tried to figure that out by using B.dA to get flux. Oh no, to get B. Wait, what did I do this to get? B.dA. Okay, this is inductance, so to get flux, because we want to use the equation L equals flux I believe. So I wanted the flux. I got that is equal to I mu naught n pi r squared. And then I solved for n. I'm not quite sure what to do from there, but I tried. Hopefully, I wanted to ask some questions.
I mean, do you have any questions regarding 53?
Nope.
No? You don't even want to try it?
Nope.
Okay. All right. That's
All
fine.
right. Thank you.
Yeah, later, Doug.